Don't say anything untoward. All right, where am I at? 7. I'm kidding about that, by the way. I'll probably say something untoward before you do. All right. 2 farads. I've got a 4 farad and a 3 farad. All right. What am I going to do?
Probably, I don't know, I'd start by finding like the total capacitance with the one in parallel.
You could do that. So the total capacitance with the one in parallel is just 7 farads, right?
Yeah.
Okay, so that's 7 farads for that area right there. What else you got for me?
And then you can find the total capacitance like of the whole loop.
You could indeed. So 1 over capacitance total equals 1/2 plus 1 over 7. And I'm going to go through that in the calculator because as much fun it is to do common denominators, there's really not much point. Boop. 1 divided by shift answer. And I got 1.55555
Yes.
per CT. 0.555. Just make one of those 6 and call it a day. All right, what else you got?
And then can you do Kirchhoffs and do the different loops?
We could indeed. Let's do Kirchhoffs and do the different loops. So which loop you want to do first? Oh, you can't show me. Okay, I'm going to do this loop first. Is that okay with you? Or I could do this loop here. Or I could do the outside loop. What do you want to do?
The first one you said.
First one. So we're going to do the inside track loop. So that's going to be 0 equals, I'm going to go up 10. Whoops, my pen is not going to do that very well. Okay. CV equals Q, so Q over C. This is Q1, so I'm no longer certain that this plate is the same as that plate because these are 2 plates here, right? So what actually is going to happen?
Wait, can you say that again?
Well, I can no longer say this capacitor is the same charge as this one. Why?
Because, well, those are in parallel.
Right, which means what?
Well, the charge is the same of like the whole parallel thing in the one capacitor.
Right, so the charge leaving this plate and this plate can only go there, right? So this plate and these 2 plates are the same. So this system and this one have the same charge, right?
Yeah.
But I can no longer say that that other one does. What did I do there? That was weird. Okay, switch. There you go. That's a 2. And then we'll call this one Q4. Oh, that's terrible. Let's call it Q2. So this is Q2. This is Q1. This is going to be Q3 in a second when we need it. All right, and then that's over 4. Okay? Can I solve that?
No.
Bummer. All right, what else you got for me?
So then you can do 0 equals 10 minus Q1 over 2 minus Q3 over 3.
I like it. Q1 over 2 minus Q3 over 3. Okay, can I solve it now? I got 2 equations.
No, because you have 3 unknowns.
Thank you. Give me another equation.
Well, this is the part I don't get because there's always like one equation with just currents.
Right. And so what's the capacitance version of current?
I don't know.
Charge. Right? Charge is what's being conserved in these little gems.
So you can do Q1 equals Q2 plus Q3.
Yes, that's exactly right. The rest is just algebra.
Okay.
The rest is just algebra. Okay?
Yeah.
Does that make sense?
Yeah.
All right. Now, the other thing you could have done, since you bothered to find the capacitance total, the reason why you find resistance total is so you can find current through that first one that's in series so we can get out of it and then do the voltage drop across the other 2.
Oh, so that'd be like finding the charge?
So you could use the capacitance total to find the charge on this one because this charge is the same as this whole thing, right?
Yeah.
And so therefore you could figure out the voltage drop across here and then use the remaining voltage drop across these 2. That's the other way you could approach the problem.
Okay, so you would just, okay, so you find the voltage drop and then you do 10 minus the voltage drop and then
Right.
you get.
Right. So if I do 1.56 CV, so I would have to do, so CV equals, oh, my pen's not working. CV equals Q, right? So then I go C is 2. I don't know what my V is for this little capacitor over here, right? But I do know that charge is going to be, no, I don't know what charge is. What would I do? Oh, I'm finding the whole thing. Duh. So I go 1.56 is my total. My voltage for the whole thing is 10. So my Q would be equal to 15.6 amps, or not amps, coulombs. Okay. Once I know that, I can do CV equals Q over here, right? Get my voltage to be equal to the Q I currently have there, which is 15.6 divided by 2, and I get that this is 7.8 volts.
Wait, what did you just do in that last equation? Sorry, I got to
No problem.
15.6.
So we know that total current, total charge being stored is 15.6, right? For the whole entire system, right? Because we did capacitance total equals voltage total times voltage total equals charge total, right?
Okay, so the whole thing has 15.6 charge.
Right.
So that means the two in parallel should equal 15.6.
These two are going to add up to 15.6, and this is going to have 15.6 by itself, right?
Yeah.
So because of that, I can find the voltage of the voltage drop across this one capacitor, right?
Yes.
So I found the voltage drop across there, and you do CV equals Q, V equals 15.6 over 2, so I get 7.8 volts, which means I have 2.2 volts across here.
Yes.
And if I have 2.2 volts across here, I can solve for the charge in this one and the charge in this one. They would have to add up to 15.6.
Yeah.
Okay? So that's the other approach. Kirchhoff law works fine. You could wade your way through these three equations, three unknowns, you'll get the same answer.
Yeah. Okay.
All right? So
Yeah,
either one of those approaches would be fine. Okay? All right. What else you want to do?
Can you do number 8 with the switches?
Do 8 with the switches. Oh, 8 with switches. That's actually a good problem. We should do that. Let me clear this up. Clear. All drawings. There we go. All right. So let's see here. 8. I've got switches. Boop, boop, boop. Then I've got switch 1. Then a capacitor. I've got switch 2. 2 farads. Probably do the same exact thing. 2 and 4, right? Well, not much for originality. It's all good. All right, it says here, just close switch 1 and answer. I'm supposed to answer what question? I'm supposed to answer what's the charge in each of the capacitors? What's the voltage across each capacitor? What's the charge across each capacitor? So if I close switch 1, I just have this funky little small one, don't I? Oh wait, I had a second switch. Duh. I just second switch over here. Let me get an eraser and see if I can. Oh, it's going to erase like massive amounts. Yeah, that's nice. It's actually a really good eraser. Unfortunately, it erases too much for my purposes. Now I got a crayon. Didn't mean to do that. Stop. Okay. Whoop. Like this. Okay. All right. So if this one stays open, right? So there's no current able to go through here, right? If I just close this one, then this whole side over here is dead, right?
Yeah.
So I'm going to end up with just CV equals Q for the charge across this one. The voltage is going to be 10, right? Because you can use all 10 volts going through that one loop.
Yeah.
So I'm going to get C, which is 2 times 10. 10 not working is my charge. So my charge is equal to 20 coulombs. Okay? So far, so good?
Yeah.
So question 1 was calculate voltage across each capacitor. 10 here, 0 here because it's not attached right now, right?
Yeah.
And then I got 20 coulombs here and I got nothing here. Okay.
Yeah.
So now we're going to open switch 1 and close switch 2. Now this has 20 coulombs. What's going to happen?
Wait, you're closing.
I open this switch, so the battery is no longer attached, and I close this switch. So this is a fully charged capacitor, and this one here has got nothing on it. What's going to happen?
Okay. Well, doesn't that mean there's just no voltage?
Is there none?
No, I guess there is.
Well, I mean, this is kind of a new idea, so I guess there isn't the right answer. It's why would there be voltage? Maybe. Look, there's a bunch of minuses on this plate, right?
Yeah,
a bunch of pluses on this plate.
For a little amount of time.
Right. For a little amount of time, that's actually perfect. That's what, like, this would be almost instantaneous. This thing would be done. Like, there'd be smoke coming out of the wires. Okay. It would be that fast. But during this time, there'd be this thing is going to discharge some of its might on this one here. Why would it stop though?
Because it runs out.
Because it runs out, not because it runs out, because it's going to keep some charge on this anyways. What's going to happen is this plate and this plate, the electrons, all they're trying to do is get away from each other, right?
Yeah.
Fundamentally, that's what they're trying to do. This is a 4 farad capacitor, so it's got a bigger plate. So a bunch more are going to go here than here. But at some point, an electron leaving here is not going to be happier on this plate. It's going to still be happier here because there's less per unit area, right?
Yeah. So
it's going to balance out. Now, we're going to balance that out using voltage, because we know when the net voltage is 0, the current becomes 0, right?
Yeah.
So we're going to say when the voltages are the same, this thing shuts down. Okay. We can also use Kirchhoff's loop law if you want to. We can say 0 equals negative Q over C plus Q over C. Why am I changing my sign for the second one?
Because they equal 0.
Right. Well, in one case, if I go this way, I'm going downhill. If I go this way, I'm going uphill, right? Also, they have to equal 0, right?
Yeah.
But so when the voltage, or you could just simply say, that's too hard for my brain. I like this Kirchhoff's law thing, but when the voltages are the same, I'm going to stop, right?
Yeah.
When voltages are the same, I'm going to stop. Now, this is going to be different than this one here, which is a little disappointing, right? Because they weren't the same. If they were the same capacitance, they'd be the same current charge, in which case it'd be fairly easy to do. I can't solve that. I don't know the charge. Uh-oh. I do know the capacitance is 2, so I could go Q1 over 2 equals Q2 over 4. But now what?
You can do something with just the like
What about the charges? What do I know Q1 and Q2 have to add up to?
Oh, they have to add up to
20, because I charged this with 20 coulombs of extra charge. There's no extra charge being added or subtracted. It's just the 20 coulombs running around, right?
Yeah.
So Q1 plus Q2 must equal 20 coulombs. That make sense?
Yeah.
And the rest is just algebra.
Okay, that makes sense.
Okay. Now this is an important trick, and it's not enough in my worksheets. It probably should be more. When you have two capacitors isolated from the battery, they are going to conserve charge, which is what that means when we say Q1 plus Q2 equals 20. They're also going to stop when the voltages are equal to each other. Okay. Probably should have like 3 more problems of that.
Okay.
Just because that comes up a little more often than when I first set up my worksheets, I thought it did. Okay.
Okay.
All right. I'm gonna briefly pause everything because I need to do this. We're gonna do numbers. We're gonna do the problems you actually asked for. Now I've wasted your time doing random problems. All right. I'm gonna pause this so I can because I get